What we're going to do today is we're going to continue our discussion of key operators in the Observable class that's part of RxJava, a key part of RxJava. And we're going to start by discussing a terminal operator called blocking subscribe, which is used to terminate an observable stream and then trigger all the processing of operators in the stream. And you'll see we'll first talk about blocking subscribe, and later we'll come back and talk about subscribe in a subsequent video. So the blocking subscribe operator is used to allow consumers, one or more consumers, to subscribe to a stream, and it also allows an observable to be subscribed as well. So you can see it takes 3 parameters. There's actually a whole slew of different overloaded operators for blocking subscribe, and we'll talk about this one in particular. These parameters are used to consume all the elements in the sequence, handle errors, and react to completions. Remember, if you think about the way that the reactive streams model works, you've got these on next, on complete, and on error event hook methods that can be called back. And these various registered parameters are used to absorb those different kinds of emissions of hook methods. This particular subscription is used for unbounded demand. What that means is it'll basically say, send me the events, publisher or publishers, as fast as you possibly can, and I will somehow manage to keep up with it. We'll talk perhaps later about a way to deal with unbounded demand, or where you need to be able to request chunks of data using a flow control mechanism. Signals that are emitted to this operator are represented by the following regular expression. You can have any number of on-next calls, including 0, followed by either on complete or on error optionally. So you might get no events whatsoever, in which case none of this stuff will run. You might get 1 on next call. You might get infinite on next calls, but you'll get either an on complete or an on error when things terminate, if they ever terminate, because of course this could go on forever. Remember, the other thing that's important about blocking subscribe, as well as the other terminal operators like subscribe, is that it triggers the processing of all the other operators in the chain. So everything's lazy up until the point where the terminal operator is reached. That's very much like Java streams. So no real surprise there. It's kind of like reduce, or it's kind of like collect, and so on in Java streams. So this blocking subscribe call will initiate all the other processing and then handle the events that come through the various parameters that are passed. In this particular case, you can see that normal processing of this example, which is going to take a bunch of big fractions in a list and multiply them by some constant. The normal behavior, the on next behavior, is just to append the results into a string buffer. If an error occurs, like an exception is thrown, such as an arithmetic exception, dividing by 0 or whatever, in that case, we're going to append error into the string builder. And then finally, when everything finishes correctly, in other words, when all the elements are emitted from the big fraction list and multiplied and so on, we're going to go ahead and cause the string builder to be turned into a stream, and then we'll display it. You can kind of think about that as sort of like end-of-file processing if you were thinking about things in a Unix pipeline-like model. The thing to remember about blocking subscribe is this call will block the calling thread. And what will happen is that thread will remain blocked until the upstream terminates normally with on complete, or an error occurs. Of course, if it never terminates, then it'll block forever, but that's probably a bug, not a feature. So you wouldn't want to have that happen normally. Interestingly enough, there's no equivalent operator in Project Reactor. They have no blocking subscribe. The only operator they have in Project Reactor is a non-blocking subscribe, just like we have in RxJava. This omission complicates some things, particularly testing and to some extent debugging, until you're comfortable using step verifier, which we may talk about later, which is a way of being able to test asynchronous code. You can also do another trick we'll talk about later, where you can make your own blocking subscribe-like mechanism using an observer. And we'll show that later on in the set of videos that we're talking about here. So that's the end of the first discussion of terminal operators. We will come back later and talk about subscribe as well. Let's continue on by covering the concurrency operators. This is going to start talking about operators that are used to arrange to run other operators in designated threads or in thread pools. And here we're going to talk about the subscribe on and observe on operators. And these are quite interesting, as you'll see in a second. So we'll start with subscribe on. This is the one that's perhaps the most peculiar in a way. And what this does is it arranges to run the subscribe, request, and onSubscribe methods in the scheduler worker that's passed as the specified or the given parameter. So you can see we call subscribe on, we pass in a scheduler. And this scheduler parameter indicates where the operations or the operators will run up into some other point. We'll talk about that in a second. So this is where things go. And we've talked about schedulers before. If you recall, we talked about the I/O scheduler earlier. We'll talk about some other schedulers in a bit. The reason why subscribe on is parameterized by scheduler is so that the scheduler classes can be reused in other parts of RxJava, such as the single class, such as the flowable class, such as the parallel flowable class. That way we can plug and play schedulers independently or orthogonally to the different types of reactive streams processing classes that are provided by RxJava. Subscribe on returns the observable that's requesting this asynchronous processing in that scheduler context. The semantics of subscribe on are a little bit unusual, and let's talk about them. When you place this operator in a chain, for example, here, we'll talk about this in a second, you'll notice we put this subscribe on method here second in the chain. What this does is it impacts the execution context of all the methods, the onNext, onAir, and onComplete signals in the entire chain, including things that came before it, which is a little bit wacky. What this particular example is doing is it's going to generate a series of values from 1 to S max iterations. Let's say that's 100, just to make it concrete. And it's going to subscribe those operations to run in a new background thread. And it's going to go ahead and do some manipulations where it's going to convert them into a big integer, which will be something here. Don't worry about the details of that. And then we're going to go ahead and print the results, and then we're going to emit it. So what's interesting here is we can either put subscribe there, or we could put subscribe on here, or actually anywhere in the chain, and it will have the same effect. Everything in this chain is going to be running in the context of this new scheduler thread. So it's a little bit hard to understand at first because it doesn't appear to have the semantics it does, which it affects the entire chain. Now, just to be complete, there's another concurrency mechanism we're about to talk about, concurrency operator called observe on. And if you have observe on appear after subscribe on, then that will change the threading context where the rest of the operators in the chain below it execute. And in fact, observe on can appear multiple times in a chain. This is wildly different from Java streams and is both good and bad. It's really cool. It gives you a lot of control over where things run, but it can be complicated to understand. And if you're not careful, you can introduce a lot of overhead unnecessarily, but you can easily introduce a lot of extra overhead. Project Reactor has a subscribe on operator that works exactly the same as the one in RxJava. And then oddly enough, there is no such mechanism in Java streams per se. You can use .sequential and .parallel to convert a sequential stream to a parallel stream and vice versa, but it doesn't quite have the same effect, especially because you're limited to the common fork join pool when you do that. Let's talk about observe on next. Observe on, for my money, is actually a little bit easier to understand than subscribe on. What this does is this says from this point onwards in the chain of pipelined operators, run those onNext, onComplete, and onError methods on this supplied scheduler worker that's passed in as the scheduler parameter. Once again, the scheduler parameter indicates what thread the operations will be performed upon. This also returns an observable that's requesting async processing, but it has a slightly different impact than subscribe on. And in particular, its semantics are more straightforward. it influences the threading context where the rest of the operators in the chain below it can execute. So in this particular case, what you see here is we're saying we want to start emitting something in some background context using create. And then henceforward, we're going to change wherever this thing was executing before, we're now going to have it execute on a new thread of control, and it will go here and check to see if these numbers are prime and so on and so forth. And so this will then change where the rest of the operations occur until either the end of the chain is reached or there's another call to observe on, which will potentially change it again. Project Reactor has a publish on operator in its Flux class that has the same semantics as observe on. Not entirely clear why they changed the names. Both Project Reactor and RxJava have subscribe on. RxJava has observe on. Project Reactor has publish on. Those two mean the same thing, but they have different names. And it's not clear why. Okay, so that's how you can control concurrency if you're going to take control of it in a chain of operators. Now, keep in mind, up to this point, what we've been doing in this class is we've been focusing primarily in this class because of the programming assignment number 5. We've primarily been focusing on the use of parallel flowables to get concurrency. So we really haven't played around a lot with subscribe on and observe on. But if you're programming with RxJava or Project Reactor, those concurrency operators have a lot of uses for other things. They're used very commonly, for instance, in Android, where there's a framework called RxAndroid, where basically you can have background operations running with a subscribe on, and then you can redirect the results of those background operations to run on the user interface thread using observe on. So it's kind of cool how that can work. Okay, let's talk about some suppressing operators in the observable class. If you recall, earlier we had talked about a suppressing operator that was called filter, which is very common. You're familiar with that already, hopefully. We're going to talk about two other ones, take and ignore elements. Take is pretty clear. Ignore elements is kind of funky and cool. So the take operator takes only the first n values that are being emitted from the upstream observable, if there are n values, and it'll stop after that point. So the parameter is the number of items to emit from the observable, and it returns an observable that's limited to size n, which is whatever you give it. This is commonly used to limit streams that are otherwise going to be infinite. So here's a simple example where we're going to generate values starting from, I think it's 0 to infinity every this many milliseconds. Let's say it's every half a second or whatnot, every 500 milliseconds. And so that'll generate in the background doing that infinitely. And what we want to do here is make sure we don't go on forever. So we're going to stop emitting after S max iteration integers are reached. Project Reactor has a take method on its Flux class that works exactly the same as take does on observable. And this should look very familiar to you because Java Streams has something identical to this as well. So you can see here that we're going to have a stream that's going to go from 1 to infinity. We're going to get rid of anything that's a even number, and then we're going to limit ourselves to the first 100 of these things, and then we collect that into a list. The next operator we're going to talk about is really funky, and it's called ignore elements. And what it does is it ignores all the items that are emitted by the observable that it's called on. It only calls on complete or on error, but not on next. So in other words, the values are ignored, but the completion or an error is not ignored. So it really should say ignore non-complete, non-error elements, but it's called ignore elements. What it does is it returns something called a completable. And a completable is a funky class that's kind of like an observable, but it doesn't emit any values. It only emits completions or errors. It only says I completed successfully or I failed. That's all it does. And you might ask yourself, why on earth is there such a thing? And I'll show you an example of where it comes in handy. So this data suppressing operator can be used to ignore its payload. Why would you want to do that? Well, here's an example. In this particular case, you can see that we're going to create an observable that's going to emit values every half a second or whatever. Then we're going to check to see if those values are prime. When we're all done processing things successfully, we're going to print the results. And then we put .ignore elements at the very end of this chain, and this is used to indicate to something that's waiting, not blocking necessarily, but waiting in a reactive sense. It can now indicate that this asynchronous operation is complete. Why would you want to do that, you might ask? Well, it turns out when we're running all of our asynchronous operations, it's sometimes very useful to have one thread that's waiting for everything else to finish. If you recall our discussion about async task barrier much earlier on in the course, the async task barrier was used to wait for a bunch of asynchronous operations to finish. How does it know that they're done? Because they call ignore elements. And that causes this notification to occur to say, I'm done, but I'm successfully done. However, that's just a signal to indicate something is finished. So you can have one point waiting reactively for everything else to finish. And of course, it'll be doing that in an asynchronous, non-blocking way, and that's reactive. So this is a very, very cool mechanism. We'll see that the async task barrier framework uses this to determine when an async task completes. And we'll talk more about async task barrier probably next class. Project Reactor doesn't really have an equivalent to ignore elements, and it doesn't have completable, but it does have a then operator that can be used in a very similar way. And that's what we use in the Project Reactor version of async task barrier to determine when an asynchronous task completes. All right, so those are suppressing operators. And I mention this stuff primarily because it's really obscure to understand how to use complete and ignore elements, but it comes in very handy when you're trying to build frameworks that are going to have one point that waits for all the asynchronous operations to complete. All right, now let's go ahead and talk about another terminal operator. So if you recall before, we discussed blocking subscribe, and now we're going to talk about subscribe. And this also terminates an observable stream, and it triggers all the processing of all the operators in the stream. But it does it in a non-blocking or so-called reactive way. So we'll see that it's non-blocking or reactive, unlike blocking subscribe, which is blocking. So the subscribe operator, like blocking subscribe, takes a bunch of parameters. It can be used to subscribe some consumers and a runnable to the observable. And these parameters will be used to consume all the elements in the stream. This is the consumer that handles the onNext calls, handle errors that handles the onNext, the onError emission hook method, and react to completion that handles the onComplete hook method. So those are the parameters that can be passed here. Like blocking subscribe, this subscription requests unbounded demand. So it says, publishers, publish as fast as you can. I will somehow keep up. And once again, just like blocking subscribe, you can think about the signals that are emitted using the subscribe operator as conforming to this regular expression with onNext, onComplete, and onError. So the API is very similar, just the semantics are slightly different because it doesn't block. What's returned here is a disposable. And this indicates that a task or a resource, which indicates a task or resource that can be canceled or disposed. And this is a little bit wonky. You'd think, why do we need this? Doesn't Java have garbage collection and so on and so forth? Well, it turns out Java does have garbage collection, but a lot of these things are running asynchronously, and so you have to be responsible for explicitly disposing of them via various disposal patterns that we'll talk about here. You can actually put all your disposables into a composite disposable object and then dispose of them in one fell swoop. So you can put a bunch of disposables and then say dispose, and all those disposables will be returned back to the free store, and any resources that they represent will be released because you're saying at that point they are no longer needed. As with blocking subscribe, subscribe triggers all the processing in a chain. So everything up to this point is lazy. In this case, we're going to omit a bunch of big fractions in a list. We're going to multiply them by a constant, and then subscribe comes along and says, okay, here's what I want you to do as the emissions come in. And when an emission comes in that's normal processing, we put it at the end of a string builder. If an error comes in, we append error. And if everything completes normally, we take the string builder, turn it into a string, and we display it. That looks pretty much exactly like blocking subscribe, except it doesn't block. So calling this operator doesn't block the calling thread. Now, what may happen is if your stream is super fast, everything may finish emitting before subscribe returns, but you can't count on that. And you typically will use this with subscribe on or observe on, so it's actually running in a totally different context anyway. Because of this, because things are not going to finish before the call returns, like blocking subscribe does, this motivates the need for the async task barrier framework, where you can actually register stuff to be called back when something is done. And that, we'll talk about that later. And you'll notice that these things take completables, and under the hood, they use the ignore element or ignore elements operators that we talked about before to inform the async task barrier that things have finished. And we'll look at that code probably next class. There's a whole slew of other versions of the subscribe operator that have all kinds of different capabilities. This is one of the more interesting ones. This will subscribe the given observer, this parameter, to the observable source instance, whatever the thing is that subscribe is being called on. And it gives additional capabilities to receive push-based notifications. So you can take control over this and do other kinds of cool stuff. Project Reactor has a slew of subscribe operators as part of their Flux class that work exactly the same or very similar to the subscribe operator that's in RxJava and the observable. And this is kind of the workhorse. Remember, as a general rule, either blocking subscribe or subscribe must always be called in order for a stream to run in RxJava. Very much like, again, like terminal operators such as collect or reduce or for each or whatnot in Java streams. Okay, let's keep on going. Let's talk about some more transforming operators. So if you recall, up to this point, we've talked about flat map, which is kind of the workhorse that you have for RxJava. We have flat map. Let's see, so we talked about flat map. We talked about map, which is the one-to-one mapping. We have flat map, which is one-to-many or many-to-one or one-to-one. You have control over what it does. So it can either have more or less or the same emissions as you have in the input stream. Now we're going to talk about flat map completable, which is this kind of interesting variant of flat map. So let's take a look and see what that flat map completable does. So it maps, or flat maps rather, an observable into a completable. Remember, a completable is something that will either return the completion or emission or an error, but the values are not going to be emitted. So flat map completable takes a mapper, and it'll map each element of the current observable into completable source objects. It subscribes to them and then waits for the completion of everything that's occurring. So it doesn't actually get values out, it just gets a completable back. And the new completable instance is what's returned from flat map completable. And this completable will then wait, doesn't have to block, but it'll wait for the upstream observable's termination event or terminal event on complete. That's really all it does. And so if it just wants to know, did everything finish? And we use flat map completable, as you will see when we talk about the implementation of the RxJava async task barrier, because we're basically waiting for completed events to occur. Very, very obscure, very, very funky. I put it in here mostly because when we look at the implementation of async task barrier, if you don't have an inkling about what flat map completable does, then you won't be able to understand what the implementation of async task barrier does. So here's a little snippet of the code, which we will take a look at later. This is the actual implementation of the run tasks method on async task barrier. So what it's doing is it's taking the lists of registered tasks, turning that list into an observable. It's then going to call the get method on each of those tasks, which will run the computation, which will run asynchronously. And then flat map completable will wait for all of these things to occur. And as you can see here, it'll wait until all the objects complete, at which point we will have a completable which will trigger when everything else is finished. And yes, I completely agree. This is very mystical and esoteric, and it took me a while to figure out how to do it, which is why I'm showing it here. And we'll take a look at it later when we walk through the code. Project Reactor has no operator that is similar to flat map completable. It just doesn't exist. However, you can use Project Reactor's flux then and mono then operators to provide a similar capability when used in conjunction with flat map. And it's really beyond the scope of this class to explain how to do that. But if you take my class next semester, we'll talk about it and you'll get to see how it works. Or conversely, you can go watch the videos from last semester's class to see how it works. So this is the way that Project Reactor's run tasks method in its async task bearer framework is implemented. Remember before, this is what the run task method in the async task bearer for RxJava looks like with flat map completable. In Project Reactor, we do something similar. What we do is we turn the tasks into a flux. We use flat map to run all the operations, and then we collect the results into a list, which is a very funky, weird list. And then we get the results and so on and so forth. And we'll look at that. You can take a look at that in my videos or wait till next semester. There's also this behavior of combining a bunch of things together is also very consistent with the way that completable futures, all of arbitrary arity method can be used to combine a bunch of asynchronous operations into a single point to be notified when they're all finished. So this is an example of the futures collector where we generate a bunch of big fractions, limit them to a certain amount, reduce and multiply them asynchronously, and then we collect the results into a single completable future. And when that triggers, when all the other asynchronous computations are done, then the sort and print list call is invoked. So very similar idea, just a slight different semantic, slight different syntax between completable futures and reactive stream implementations. Okay, so that's the overview of another transforming operator. There is yet another transforming operator that we'll take a look at probably next class, which is called flat map observable, and we'll discuss that when the time comes. The next example I'd like to take a look at is one of the scheduler classes. This is the computation scheduler. And so schedulers is a Java utility class, computation is a factory method on it, and that can be used to create an appropriate thread pool that's a fixed size thread pool used for computation. And the nice thing about the way it's designed with RxJava is this works with flowables, parallel flowables, singles, maybes, and so on. So it works for all the classes. They can be parameterized by the type of scheduler. So scheduler's computation hosts a fixed size pool of single-threaded executor service-based workers. That's just what they decided to do. Not quite sure why. Probably ask ChatGPT to explain it. And the new scheduler is suited for parallel work, and it's optimized for non-blocking executions that are going to run relatively quickly. That, in other words, it's meant for compute-bound or CPU-bound tasks, not I/O-bound tasks. If you want to use I/O-bound tasks, you should use the I/O scheduler, which you get with the schedulers.io factory method instead of the schedulers.computation factory method. So we typically use the computation pool for event loops, callbacks, computationally centric work. So here's a simple example, much like what we've been looking at, where we are going to multiply a list of big integer objects in a background thread in the computation thread pool. So you can see in this particular example, we take the list of big fractions, we use the flat map concurrency idiom, and then we have the inner stream running those computations on each of the big fractions in some thread from the computation thread pool. And then when we're all done, we're going to go ahead and reduce everything. So you can see here, this is what's called a lazy factor method. This is, by the way, this is an important point. So when we run this operation in the background, then the multiplication is actually going to occur in the context of the computation thread pool. If we replaced observable from callable with observable just, it would not run in the background. It would run in the main thread, which would be completely bizarre. So got to be very careful and make sure you use lazy operators if you want to have these computations running in the appropriate thread pool. And then when we're finally done, after everything else is finished, the final thread that finishes its computation will then be the one to perform the reduction. So all the other threads are just go back to being in the pool, no muss, no fuss, and the final thread is what runs the reduce, and then, of course, that will return the value here. Internally, the computation thread pool is implemented using daemon threads. Remember, daemon threads in Java mean that the threads will exit if there are no other non-daemon threads remaining. So if, for example, there's the main thread, what's called a user thread, a pool of daemon threads, for example, in the computation scheduler context, and the main thread exits, all those other threads shut down. Now, if there's another user thread, they'll continue, but daemon threads don't survive without having a non-daemon thread around, a user thread. The scheduler's parallel operator in Project Reactor is very similar. It's intended for compute and CPU-bound tasks, not I/O-bound tasks. So be aware that that's a distinction. There's something in Project Reactor called bounded elastic, which is intended for I/O-bound tasks. And we also are familiar with Java's common fork join pool, which works for CPU-bound tasks or compute-bound. With the common fork join pool, of course, if you use manage blocker, it'll also work on I/O-bound tasks, but that comes extra. So that's the end of the discussion of schedulers. We've talked about I/O schedulers. We've talked about compute schedulers, computation schedulers. There's a bunch of other schedulers in RxJava. We're not going to talk about them, but just be aware that they exist. So if you're ever in a situation where you have to really understand RxJava, you might want to take a look at the schedulers documentation, which will tell you the full range of schedulers that they provide. Let's now talk about some operators that have to do with combining, or we'll start off by talking about one in particular, which is the reduce combining operator. And what this does is it creates a maybe, kind of a funky name, a maybe, by accumulating the elements in an observable stream. And the reason it's a maybe is because if there's nothing in the stream to begin with, then maybe there won't be a result. Maybe there will be a result. Depends on what's in the stream. So here's reduce. Reduce should seem familiar to you because there's a reduce operation. It's a terminal operation defined in Java streams. The reduce operator in the context of RxJava will reduce the values in an observable stream into a single object, which is the same type as the types that are being emitted. And the reduction itself is performed by a bifunction. So as you may recall, a bifunction is used to take two operations and reduce them or do something to them, and then it'll go ahead and return a result. The parameter that's passed, this parameter, this reducer, is passed as the intermediate result of the reduction and the current value. So for example, let's say we're going to have an observable with integers from 1 to 4. Very simple, but makes the case. So we'll start out with the initial value of 0. 0 plus 1 is 1. 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. That's a simple example of reducing by addition. So it'll return the intermediate results, and this process continues till you get the final reduced result, which in this case would be 10. So the final result is emitted from the final call as the one and only item of a maybe. And you can see that maybe either gives you a value or it doesn't give you a value. So if there's nothing there, it doesn't give you a value at all. An empty maybe will be returned if the observable emits no items. So if you have an observable that's 0 sized for whatever reason, because the list you gave it or the input source you gave it didn't have any values or elements, then you'll get an empty observable. An empty maybe. The value that comes back here, if error or cancellation occurred, is just discarded. So remember, it's doing incremental reductions, but if an error occurs, those incremental reductions are just ignored. Here's an example of how this needs to be used in practice. The upstream, whoever's calling, or who's ever supplying or emitting data into the reduce operator must signal on complete. Otherwise, no value, no final value will be emitted. So here's a simple example where we're going to have an array of big fractions. We are going to multiply those things in the background using the computation scheduler. We'll talk about that later. And then we're going to reduce these multiplied results by adding them together. If this stream never terminates, this stream will terminate because there's only a fixed number of elements in the big fractions array. But if it doesn't if it does terminate, we'll have the results of summing the asynchronous multiplications. But if there's no completion, then nothing will be emitted. It'll run forever. And chances are, no surprise, you will eventually run out of memory because it'll just keep incrementally absorbing these things and reducing, trying to compute the results, but it'll never complete because it doesn't have the on-complete signal. So you'll probably run out of memory and get the fatal out-of-memory error, which is bad news, especially in Java. Project Reactor has a reduced operator that works exactly the same way that things do in RxJava. And there's a reduce operator, reduce operation, terminal operation in Java streams that also works in much the same way. So in this case, we're going to have a list of values. We turn into a stream and reduce them by summing up all the values in the list. So very similar, a few subtle differences between reduce in the RxJava or Project Reactor, reactive streams models versus streams. Most notably in RxJava and Project Reactor, this is all typically done asynchronously, whereas in streams, it's typically done synchronously. So that's the end of the discussion of combining operators. So let's move on now and talk about another set of combining operators, collect and collect into. These operators, very much like Java streams, where we have reduce, which returns a value, typically a primitive, and then collect, which returns an aggregate collection of some kind. So too in RxJava do we have reduce that typically returns a primitive of some type, and then collect into and collect, which return collections. There are some subtle differences, however. So let's take a look at these. It's kind of interesting. We'll start with the collect into operator. This will collect all the items that are emitted by the finite source. In other words, we can't let this run forever, otherwise we'll run out of memory again. And it'll put them into a single mutable data structure. And what you're passed here is the initial item that you're going to collect or accumulate the data into. That's the first parameter. Mutable, meaning it has to be updatable. So here, for example, we're going to use an array list. And then the second parameter is a by consumer that's used to take an item from the stream and then do something to it to add it to whatever the initial item is. So in this particular case, since we made an array list, then we're going to use the add method to accumulate the results into the array list. Pretty straightforward. So that's what collect into does. And it returns a single, which is another one of these special classes in RxJava, that emits the results of doing all this collection. This operator is a simplified version of reduce that doesn't need to return the state on each pass. It just collects things into that mutable data structure passed as the first parameter. Here's a simple example of what we might do. We might take a big fractions list, turn it into an observable, flat map it to do something to it. Then we're going to go ahead and filter things that have values greater than 0. And then we're going to collect the results, the non-zero results, into an array list of big fractions. And we're going to add the results together. So we're going to end up basically appending them together to create a new array list or a new list. Project Reactor does not have collect into, but it has a method called collect that works the same way, or very much the same, very similar way. And there's also a collect list method, which is a more concise, although a more limited option than collect into because it's restricted to only having a list, whereas collect into could use some other data structure besides a list. All these things are very similar to Java Streams collect. In fact, they use the same collector mechanism that Java Streams does. Here's an example where we have a list of integers from 1 to 6. We turn into a stream. We go ahead and collect even integers. We ignore the odd integers. We collect even integers, and we put them into a list. Let's talk about collect next. I'm not honestly sure why collect into is all that necessary. I guess there's some use cases. But collect is a more familiar interface, a more familiar operator that is part of RxJava. This collects the finite upstreams values into a container, and the parameter is the good old Java stream collector interface. We've seen this now for quite some time, going back to our initial discussions of Java sequential streams, and the Java parallel streams, and the Java completable futures. We've looked at collectors over and over again. And if you recall, collector is this interface that's parameterized by the type of the stream, the type of accumulator, and the type of results. And it's got a bunch of factory methods like supplier, accumulator, finisher, and so on. And so this will return a single that emits the container, whatever was being collected into. And I just find that to be a bit more intuitive than collect into and a little cleaner. So here's an example of how you might use this. You might generate a bunch of, in this case, say big fractions up to a certain number, do some operations on them, and then collect them into a list, and then do something when the list is finished. So that looks very much like Java Streams. In fact, it's built on the Java Streams collector interface. It's similar to the collect into mechanism, but you can provide your own collector, so it's arguably more generalized. And then the collect operator in Project Reactor's Flux works the same way. Collect list is more concise, but only works on lists. And this all is very similar to Java Streams collect. This, just for kicks, I changed this to collect into a set as opposed to collect into a list, but same basic idea. You can do the same kind of thing by passing in the appropriate collector factory with collect in RxJava and Project Reactor. Okay, so that is the discussion. That's the end of the operators that I wanted to cover today that we hadn't covered last time. Be aware that I don't know if you need to use many of these operators for programming assignment number 5. However, if you program with RxJava, these operators are going to be very familiar and very common. Not many programs in practice use the flowable, parallel flowable stuff that we're doing for assignment 5. The stuff I talked about here is a lot more common.